This question says, a sound wave is easier to represent using a graph of the pressure. Here the graph is of pressure in the air against a position. This represents a snapshot at one moment in time. Label the wavelength, a compression, a rarefaction, and the amplitude. So again, the wavelength is the distance between two identical points in the wave. I'm going to label that down here at the bottom, between two troughs, again, using the symbol lambda. So for a compression, we can see in the middle of the graph here, we've got a pressure of 0. So presumably this is talking about how much the pressure has changed from the normal value. It says it's in arbitrary units. So if this is sort of the pressure of the atmosphere, right across here in the middle of the graph would indicate the air being at normal atmospheric pressure. Up here, we can see that the pressure has increased by one of these arbitrary units, whatever they might be. So the peaks at the top here represent areas with a higher pressure than normal, what are called compressions in our longitudinal wave. Conversely, down at the bottom, we can see the pressure is lower than expected at these bits down at the bottom. So I'm going to just label 1 over here, but obviously each of the troughs is a rarefaction. Then lastly, the amplitude. So the amplitude for a wave is defined as the maximum difference from the equilibrium value. So on this particular setup, this here represents the amplitude of this sound wave. Obviously, we could label it on either side. So I'm going to draw another arrow here. I'm just going to label this one the amplitude. The amplitude of a sound wave would be given by differences in pressure. Now, because we haven't got a proper unit, we could say that this one has a value of 1.0 arbitrary units. This could be pascals, perhaps, or kilopascals, perhaps more likely, for a real sound wave.